Okay, fantastic, Michael. Please.
All right. Thanks, Sam. Yeah, I was trying to choose what to talk about for this, and I decided some unpublished work would be fun, but hopefully it'll be published like by Friday. I don't know. Depends if we're satisfied with dotting our I's and crossing our T's. But yeah, so the topic is, as Sam was saying, we're going to talk about, trying to figure out how to adapt things in generative modeling for problems like sampling from unnormalized densities or fine-tuning generative models. Okay, and so the way I want to lay out this, quasi chalk talk, I don't really know what to call it, iPad talk, um, is sort of introduce this notion of dynamical measure transport, building maps between distributions in a dynamical way, which has been a hot topic in machine learning these days and has lately become a topic in sampling. And then I want to sort of motivate the challenges in sampling and fine tuning that are different from generative modeling, namely that we don't have data a priori to learn from. And I'll sort of give, a little picture of how both of these problems can be phrased as tilting a previously existing map. Okay, and then we're going to look at the equations governing this tilt and show how they can be used to learn how to adapt the dynamical equations, right, so that we can sample the new distributions we care about. Okay, and hopefully the story will be fun. There's, it's a very simple story, but and the important practical parts are very straightforward, but there's some side interludes that are kind of interesting maybe for the statisticians. Okay, and then I'll talk about why it's actually beneficial to do this. And so this is work with Peter Potapchik, who's a PhD student at Oxford, visiting me for an undetermined amount of time, but currently still, so long as the US government allows him to stay. And then Brian Tripkit Lee, who is with us for the summer and hopefully will return sometime in the future. Okay, sound good? Okay, so, right, generative modeling. I'm just going to give you this little overview slide that I give all the time, which is to say, what's our goal in generative modeling to see how we'll adapt that to the case of sampling and fine tuning. Okay, usually what we want to do is estimate some unknown probability distribution with some density rho 1. I'll interchangeably use density, distribution, etc., refer to them in the same way. And what we do in generative modeling is we learn this through sample data, x1 from some rho 1, okay? And the one here will be apparent in a little bit when we introduce the dynamical time-dependent formulation of this, but our target, is this rho 1. Okay, and if we look at the historical development of this topic over the past 15 years, 13 years, at least for like continuous valued data, things that are not on some discrete state space, in 2012, we were able to, generate these MNIST digits of threes in sort of a low complexity, maybe simpler setting. And as both compute and methodology has improved, now I tried to ask Veo3 to say that we're all just prompt engineering now, and this whole world's a simulation. But for some reason, it misinterpreted it that I was a revolutionary who was trapped in a dungeon. So we still have a little ways to go in terms of prompt adherence, but it's pretty crazy that you can write this prompt and generate this video out of nowhere now. And what I kind of want to stress is that the underlying methodology associated to this, revolution has deep ties to what, we've historically called in applied mathematics, measure transport, building maps between distributions. And as the measure transport has appeared more and more underlying these sorts of methods, we've seen this sort of vast improvement. And so what I want to just make sure we're on the same page about before going forward is, what do we mean by measure transport, and how can we adapt the governing equations in this sort of domain to create more understandable and performant tools, and in particular, in this case, borrow from the methodologies that have been successful for generative modeling for the harder cases, I would argue, where we do not have data. Okay, sound good? Okay, measure transport. The simple picture we'll keep in mind is sort of building maps between distributions. Okay, so if I had some very simple base distribution that was easy for me to sample, okay, which I call here rho 0, right? It's the density rho 0. And I can draw x0 from rho 0. Maybe it's a Gaussian distribution like this little pictorial example here. I want to learn some map that goes from whatever space I'm in to whatever space I'm in that assigns every sample under rho 0 to a sample under rho 1. Okay, so if I have this like totally random pixel image under some, Gaussian, high dimensional Gaussian, I want to be able to assign that to be an example for, in this case, the images of flowers that are, 256 by 256 resolution, etc. Okay, so that is to say, row 1 here is defined by the map connecting row 0 to row 1. Okay, so this map T is what we care about. And one particularly effective way people have realized these maps in practice is to construct them as the solution to some dynamical equation. Okay, so what we want to imagine is that x0 is continually deformed or evolves over some time domain, maybe just from t equals 0 to t equals 1, hence the labels, so that over time it's continually deformed to become some x1. Okay, so for abusive notation, imagine we have here is a time axis is the x-axis in this sort of domain, and I can, in this one-dimensional picture, I could be positive or negative, which I'm showing here on this axis here, and all of my little samples are initially distributed under row 0 here, and I have my random Gaussian, and then I can track these characteristic curves, okay, which typify the evolution of any initial condition along a path through time, evolving in x, right, to be a sample ultimately under row 1. And the object governing this evolution is some velocity field, okay, that tells us about its instantaneous change. So if I look at xt, which is the x value here at some time t, mislabeled because I don't know, I didn't put a t here, but imagine this is time t, right? I'm looking for sort of the tangent vector to this point along this trajectory, so as to govern its evolution by integrating what we would refer to as this probability flow ODE. Okay, that says if I take a sample x0 under row t equals 0, and I solve the ODE governing the time evolution, denoted here by a dot, of xt, okay, then what this will amount to is integrating some velocity field over time and under some sort of Euler discretization or whatever you choose, right, if you have some fancy solver, okay? The point is that BT defines how xt should instantaneously evolve. Okay, and that's going on for every x, i.e. every particle, right, every sample. And we can ask also what must be happening at the level of the distribution itself, okay? So this is the evolution of the samples. What are they doing in aggregate? Okay, and the density needs to satisfy some sort of continuity equation. That is to say, the time evolution of the density is related to this velocity field and the density itself. And this is, let me decline that call. And I go back here. Is related to this density itself, right? And it's just basically a mass preservation type argument, okay? Okay, but the question we have in generative modeling is, how do I choose a row t, the sequence of distributions that connects row 0 to row 1? And then how do I learn the velocity field associated to that so that I solve this continuity equation and thereby guarantee that samples evolving according to equation 1 actually produce samples under row 1 at their terminal point? Okay, so just as some quick background, one handy way to go about doing this is, what we call either flow matching or stochastic interpolance. Okay, and that is to say we can implicitly construct a row t as the law of some stochastic process that arises purely from the data we have available. So I have samples x0 for my base, I have samples x1 from my target, okay? And it turns out that if I draw them according to some coupling, maybe randomly and independently, but maybe they have some, shared coupling that I sample under, and I construct this simple interpolating object, that is to say I have some alpha t, maybe like 1 minus t, and beta t is, maybe t, okay? And I have the boundary conditions that at time t equals 0, this interpolant it will evaluate to x0, and at time t equals 1, it'll evaluate to x1, okay? Then under the sort of stochastic drawing of x0 and x1, the law of it is some row t, okay, that connects row 0 here to row 1. Okay, and it turns out that the BT associated to this row t, right, such that I can guarantee that 2 is satisfied and therefore I could use 1 to produce samples, has a closed form. It's just not one that we have, immediate access to. And the BT, the velocity field governing the transport, is just given by the conditional expectation of this interpolant, its time derivative, conditional on the fact that the interpolant is equal to x. Okay, so what does that mean pictorially? If I wanted to know what BT was at this point, I would look at what happens for every random draw of x0 and x1 I take from the base and target. I draw the lines associated to those, those interpolant realizations. And I say, if I look at the average slope of the lines that go through, what did I just do? I accidentally almost deleted something. All right, we're going to roll with it. Oh, there we go. There we go. And I look at all the lines that go through this point, conditional on that the interpolant, right, is equal to x at this point, then the average slope of that line is the velocity field. Okay, so you can, you would be able to, in some low dimensional sense, estimate this with Monte Carlo. But what is really more useful to do is learn BT over neural networks by just saying, I'm going to regress a BT hat against this interpolant just by using the Tower property of conditional expectation that says, if I plug this conditional expectation into some regression loss, and I'm taking the expectation over x0 and x1, okay, then Tower property says I can get rid of this conditioning, and I just need to do BT hat minus IT dot squared, okay? Okay, and then the minimizer of this objective is this guy. I learned it over neural networks, and then I can use the BT coming from 5, the minimization of 5, to perform sampling, right? So I can generate samples using this probability flow ODE. That is to say, draw an initial condition x0, let it evolve. Maybe in this case, I'm going from Gaussians to flowers, okay? And we can go on from there, okay? And you also can get the score from this if you'd rather use an SDE rather than an ODE. But okay, we know this works very well at scale, and the limitations we want to now try to address is to say, how do we learn such a map for sampling wherein I don't necessarily have data originally, but I know energy function or some unnormalized distribution? Or relatedly, how can I adapt the BTX to fine tune an existing generative model? Okay, and I'll show it, suggest that these are dual problems to each other in terms of the sort of learning setups we have here. I mean, maybe another example is like inverse problems and posterior tilts like this, but we didn't show any examples of that yet in the paper. Keep that in mind. Okay. So fine tuning and sampling as tilting. Okay, and now we'll get to sort of the meat of what I want to talk about today. So imagine we've learned a generative model for some rho 1, okay? Maybe this is a high temperature Leonard-Jones system, so you can just produce the Monte Carlo data and then perform flow matching on the Monte Carlo data. This is something you could do. Or maybe this is an existing generative model like Stable Diffusion, okay? And now someone has given you a new target, okay? It's the same distribution, rho 1, but now tilted by some reward function, some exponential tilt. Okay, so R in the case of sampling would define the new energy function that you want to sample under. So maybe it's a lower temperature Boltzmann distribution, wherein there may be more strict multimodality or metastability if you were going to run some local Monte Carlo algorithm. Okay, or R is a giant neural network, which helps you rank or measure the quality of the output of your generative model. Okay, so one common thing is like prompt adherence in big generative models. I give you a text prompt, I give you an image, and people train other neural networks to say, given both of these, rank how well this aligns with the text prompt, okay? And so here we're dealing with something that's some gigantic thing. We're evaluating, for example, the gradient of the reward is costly, okay? Here, maybe you're fine to do that, right? But in both cases, the data is not available for these setups. I don't have samples from the tilted distribution. I don't have samples from the low dimensional Boltzmann distribution, and I don't have samples from the improved image generator. If I did, I wouldn't be trying to rank the outputs and fine tuning the model, right? So these are data scarce settings, we could say. Maybe you have some samples, but we'd like a method that works a priori with none initially. Okay. Okay. What we know is that these flow matching and interpolant transport plans, like this guy up here, have some smooth regularity properties. And that is to say, if this loads, this guy has some smooth regularity properties. The velocity field is never changing dramatically. Its scale is always decently well controlled as far as, okay, it's hard to estimate this stuff when there's giant neural networks, but we know that there aren't like, horrible discontinuities in these transport plans and stuff like this. And we know that they work very well when the base distribution is a Gaussian, or, some distribution that you know how to sample quite well. And so what we may want to ask is, how does the velocity field BTX, that was the solution to our original transport problem, related to the velocity field BT, I'll call it hat for abusive notations, just to align with the fact that I call this rho hat, to the tilted distribution, right? We want the velocity fields between these two plans to be related, okay? And one way to go about asking about the relation between BTX and hat BTX is to introduce some sort of annealing into the tilt, okay, and expand the dynamical space under which we consider transport, okay? So if before I was sampling row 1, now I want to sample some row 1A, okay, where A is just indexing how much I've like brought in the tilt, okay? So I have row 1x weighted by e to the a r of x. So if a is 0, I'm doing my original generative model going from row 0 to row 1, a equals 0. This is just, no fine tuning and just the original, maybe, flow matching problem for my sampling problem. And what I can do is now dynamically bring in this tilt, right, by annealing in a. So at a equals 1, let's say I'm fully doing my tilted sampling problem, and at a equals 0, I'm not. And for all of these, I'd like to learn transport plans that go from the Gaussian, okay, to these different targets. So that is to say, before we had a BTX, and now we have a BTA of x, which is basically to say we're defining a velocity field indexed by two, one parameter families, right? There's t and a, and there's some, their plane under which we'd like to know all of them and how they relate. Okay. So, okay, trivially, right, ideally one thing one would do is just to say, okay, well, if I want to learn BTA, let me just construct the stochastic interpolant that now uses samples x1a, right, from row 1a, and just go from there. But this is, a total non-starter because we don't have the x1a, right? If we did, then we wouldn't be phrasing this problem to begin with, right? So all we have is x10, and we'd like to construct an iterative procedure that gives us BTA for all a, starting from BT0, if that makes sense. You with me? Okay. Okay. So someone, basically figured this out, I guess, in the 30s. And it's really just an application of the Escher transform. And that is to say, how do, expected values of certain functions evolve under exponential tiltings? Okay, so this person was thinking about this for risk analysis and financial stuff. Okay, but I mean, it's an exercise maybe worth doing, but it's really just reweighting the interpolant velocity. So if I have IT0, right, which is the interpolant I'm indexing now with a equals 0, right, from the original problem, which I do have data for, because that's either easy to run Monte Carlo or it's the original generative modeling problem, okay, then BTA can be defined with respect to only samples IT0 by the following reweighting. And that is to say you take IT.0 weighted by e to, this should be, let me make a small correction here. The benefits of doing this on the fly is that those should be A's, okay, not H's. Is just that you take the interpolant now weighted by the reward, and then you normalize, okay? And trivially, if I want to know this not from a equals 0 to a, but for any a to any a plus h, I mean, the same formula holds, but now this guy has the e to the hr in the exponent instead of a. Okay? So a little proposition you can write down from this just by using the quotient rule, taking h going to 0, and then basically writing the time derivative of b with respect to a, says that this augmented drift actually satisfies an ODE. Okay, and the ODE is to say that dB is equal to the conditional expectation of the time derivative of the interpolant times the reward, minus the conditional expectation of the interpolant, which is my original velocity bta, times the conditional expectation of the reward. Okay, and the right-hand side of this equation is exactly the conditional covariance of the time derivative of the interpolant and the reward. Okay, so there's some sort of, statistical notion here that relates this random, stochastic process to the reward and tells us how the velocity field should evolve. And what we're going to do is manipulate this equation for the rest of the talk to come up with a learning procedure for BTA that does not require gradients of the reward function with respect to its input and does not require trajectories, i.e. solutions of the ODE at all times to do the learning. And it'll be some simple regression objective that actually has better variance properties than the original stochastic interpolant picture itself. Okay, that's going to be what we're aiming for. So pictorially, what this equation is telling us, equation 8, is that if I had some transport from a Gaussian to my target over here, with this written in gray here, that's my original generative modeling paradigm. And then I want to learn how the solution, the BTA at all times and for all x along these trajectories, is exactly related to the solution for another interpolant transport problem. Then I want to exploit this equation. Okay, if this is B here over as I move through A, right, maybe it goes from negative to positive, pushing up versus down along these trajectories. Okay, so what's one way that we can use this to learn BTA? I'll talk first about a very explicit and sort of trivial way of doing this, is to say if I expand BTA plus H to first order, okay, then I have BTA plus some H dBdA, right? Plus some order H squared correction. Okay, and I know exactly what dBdA is at this point, because we just defined it above with that covariance ODE, tells you how B was evolving in A. And so I know that this is just a drop in. I'm going to put H times the covariance that I was just referring to above. And because these are all conditional expectations, what I can do is write down some residual operator that functions a lot like what the original interpolant was doing, right? The original velocity field was some conditional expectation, and now the correction to that velocity field is also some conditional expectation, which means I can write learning the correction as the minimizer of some quadratic, L2 regression problem, right? And that is to say, if I extract a residual operator here that I call T, and ETM, because this is an explicit discretization that allows me to perform what we'll call tilt matching, because it's matching the tilt of the velocity field to solve the tilted transport problem. Then what I have is this operator BTA plus H times all the things inside the conditional expectations. And if I try to match a new BT that's taking me from A to A plus H, okay, against this residual operator, okay, then the minimizer is just its conditional expectation, which is exactly the correction up here. And it's the first order accurate solution to 9. Okay, that tells me how I need to adapt BTA plus H to perform the sampling. Okay, and then if I iterate on this with H small and going to 0, then I would recover BT1, A equals 1, right, which is the solution to my tilted transport problem. Does this make sense? Any questions?
So just to clarify, so the current thing is you've solved it at A and you're looking to bootstrap that into something at A plus H, basically.
That's right.
Okay.
And if you solve each of these minimization procedures, then you'd get to A equals 1.
Yeah.
Right? Of course, you could also learn over A, have some generative model that learns both, but coding-wise, it's just easier to do it in an iterative fashion, but both are totally valid.
Cool. Thanks.
Okay. So this is a regression objective that only requires evaluating the reward, has no derivatives in it, just this quadratic loss function. But there are two little issues with it. One is that you can have this compounding error, which I was just saying to Sam. It's like, okay, if you don't solve it perfectly at each case, there'll be error. Okay. This can be fixed with reweighting. There's just weights that you can stick in these objectives that ensure you're always doing the right thing. And the second is that there's this discretization error in H, right? If I don't take H actually at, formally at 0, then I'm always having these order H issues. And you can argue about whether or not this is important. Maybe you can take h so small that it really doesn't matter. But it would be nice if we could just get rid of the discretization error entirely and maybe do something that has, decent variance. Okay? So let's try to solve 9 to all orders and learn what the correction would be. So if I do the trivial thing and I just say, okay, let me do the full all order Taylor expansion of what BTA should be, BTA plus H should be. Okay, then I just get this infinite sum here, where I'm getting higher order derivatives on B with respect to A, right? So it turns out, you can just show this by looking at the moment generating function of this guy, that for the BTA that is given initially, as ITA dot, right? We know this for A equals 0, but this holds for any A. Then the nth term in this expansion actually has an interpretable meaning, and it's the n plus 1th order joint cumulant of the interpolant and the reward function, or n copies of the reward function. Okay, so if I was trying to correct BTA, to some BTA plus H, to first order, this is the covariance of the interpolant and the reward. And then every higher order term, that goes into this is the next cumulant and the next cumulant and the next cumulant, with smaller and smaller contributions. Okay, so if you really cared about getting rid of the discretization error, one thing you might do is try to, learn more and more of these terms. But then maybe your expansion is getting ugly, and the target, operator you want to match here has all these extra terms that is getting ugly, and you need to have, you need to match every one, which means you need more and more samples and blah blah blah. We would love to use this fact to learn something that is discretization free right off the bat. Okay. So there's a way to do this, and we call it implicit tilt matching. Okay. And the idea is that if you rearrange that Escher transform that I talked about above, and I like to put little purple circles on these guys. Oh, but it's just wrong. Oh. Okay, that's good enough. If you rearrange this Escher transform, basically you just bring the numerator over to the left-hand side and subtract. You get this optimality condition, okay, for learning BTA plus H, right, for any H. And that is to say, any objective function should ensure that this is true, right, for your candidate BTA plus H. That minus the interpolant reweighted, right, should be equal to 0, because these expressions are going to be equivalent to each other. Okay, so what is also true is you can introduce a control variate to this equation. And that is to say, it's enforcing the same thing, but if you learn it over Monte Carlo estimations, its variance may be different. Okay, so if we put the right C of x in here, which is our control variant, we can have this augmented optimality condition that basically says the area of greatest variance in our objective function is going to come from taking random draws of the interpolant, because the other terms are going to be just, the differences between the velocity fields themselves. And this isn't a Monte Carlo estimator. Remember, this thing has this conditional expectation effect in here. So what we want is this e to the hr x1a minus our control variant to be as close as possible to 0, so that this term matters the least in enforcing any objective function, in any objective function enforcing this to be true, right? So, okay. Well, one simple observation is that if h is small, right, then this quantity is close to, 1 plus hr even 1, if we take h to 0. And then we would really just want c of x to be equal to 1, right? Because then this will just give me some sort of 1 minus 1, or 1 plus hr minus 1, something small if h is really small. Then this term doesn't really matter, and we have a strictly better variance objective function. Okay? But it turns out there's even more to interpret in this case. Okay. So we plug in c equals 1, you get an objective that, an optimality condition that looks like this. All I did was get rid of this and put this equal to 1. If I rearrange these terms, I get an expression for BTA plus H minus BTA, right? But that is particularly exactly equal to this sum, this infinite expansion here. And so that means we're going to end up with an expression for what this sum is equal to, i.e. what is the sum of all of these cumulants? Okay. And that is to say this sum is actually just equal to this term over here. And I missed every single parentheses in this guy. Okay. Which means that there's an exact way for us to try to match what the correction would be, a residual for the correction to all orders. Right? So if this is the correction to all orders and then it's given by some conditional expectation, well, now we're in a avenue to ask, can we write in a regression objective for this, just like we did for the explicit discretization case? But what is funny here is that this expression depends actually on the solution. Okay? So this is looking a little bit like some sort of implicit discretization scheme, right? Where we have we're looking ahead to what A plus H is, even though what we're trying to learn is A plus H. Okay? So if I write down some implicit target operator, which I botched here because this needs the e to the hr x1a minus 1 term in front of this, and I replace this guy with any estimate bt hat of what A plus H is supposed to be, okay, then I can write down another objective function that is in terms of this implicit operator, which is saying I'm trying to match bt hat against this guy, where I replace bt A plus H with my guess of what the current solution is. So this is kind of like some implicit tilt matching, okay? It's an implicit method because the target residual actually depends on the solution. But if you put a stop gradient on this guy in the right spot or rewrite the objective a little bit, you can show that this is a totally valid way of doing the optimization. Okay, but what this gives us is, this will give us the BTA plus H for any H and is discretization free. Okay, so this would actually solve the transport problem that we want and relate the right equations. Okay, so I'm going to quickly go over some examples. Maybe I went a little too quick on this, but I just wanted to tell kind of a short and sweet story. I don't really know how to interpret the cumulant stuff, but maybe the statisticians would be like, oh, cool, I know exactly what the implications are of this. We just thought that was an interesting little aside. It's not really important for the analysis, for the numerical implementation of this guy. But if you want to sample some Leonard-Jones potentials, which is something people like to try to test any new neural sampler, quote unquote, on, what you may do is run some very high temperature molecular dynamics simulation where you can cover all the modes because everything is there aren't really any modes, and then set that as your initial baseline model where you learn a flow matching model on that data, and then you lower the temperature by increasing A, by introducing the tilt until at A equals 1 you're at your final temperature. Then this is a way to set up doing sampling of Leonard-Jones potentials. Okay, and we found that this is both the ETM and the ITM version of these algorithms work pretty well in this case. I think we're starting to really get non-trivial ESSs on these problems now, effective sample sizes, right, for your sampler. And yeah, I guess, you can sort of check that other interatomic distance measures, stuff like this, are really holding well. This is for the LJ13 case, and then the LJ55 is a bit harder of a problem. It seems like we've made some progress there as well. In the ETM implementation, we sort of measure if the ESS is dropping too quickly based on the size of the step, because it can compound discretization errors. So it's, there's an adaptive way of choosing the step size that ensures that you're not going too quick. But if you don't want to compute the ESS during the training, then the ITM, you basically know that at all times you're doing the correct algorithm. It's just whether or not you're moving slow enough, right? And so the ITM is something that scales a little bit better. For example, if you're trying to compute the ESS for the ETM adaptive step size, and the ESS requires the divergence of a big neural network to be computed, well, this just doesn't scale well, and the algorithm will be slower. So we didn't even really bother to test it on the LJ55 just because the system is so much bigger and this seemed to work. But these concerns are really only more important for sampling than fine-tuning, because fine-tuning is already the Wild West. The idea of being quote-unquote exact doesn't really make sense because we don't even know. We've chosen a heuristic of what the target distribution actually is, because the tilt is with respect to some gigantic neural network, and there's not like a real measure of what success is other than other human preferences that you may compute downstream. But what we did is we just took stable diffusion as people are doing these days and trying to fine tune it with different reward functions. One of the common reward functions is something called image reward. Okay, and that is exemplified above in this little picture I showed earlier. And that is to say, I get a prompt, a painting of an ocean with clouds and birds, daytime, low depth of field. You give a bunch of example images to this guy, and it rates them according to how well it aligns to the sentence. Okay, so this is some gigantic neural networks that people trained with some, contrastive learning algorithms such that these things work. And people use it now as the reward function to do fine tuning. And so we built on the code base for the adjoint matching paper that Carles, Domingo, and Rick put together. It's a good little code base in case you want to use it. And basically the idea here is if I take samples from the baseline stable diffusion model, according to the prompt here, for example, cute cats, plural, in a conceptual art style. Well, one thing to note is this cat is not so cute. It has kind of demented eyes, and it's not plural. There's not two cute cats. So, what you would hope is that after doing the fine tuning, you actually adhere to the prompt better. So if we employ this tilt matching algorithm by just, doing this fine tuning for a few hours on samples coming from the base model, we can, effectively adhere to these prompts. So for example, retro sci-fi art of an astronaut next to Jupiter in a car. Okay, well, the astronaut is not next to Jupiter and is not in a car. And I guess now you can argue he is. Likewise, with this field of light blue lotus flowers that's minimalistic art and elegant, none of these flowers are actually blue, but the grass around them is. And here we can make the blue flowers and actually have them be lotuses. And then what you do is you don't want to actually just overfit to image reward because all of these are sort of hacked together measures of success. And so what people do is they have many variations on this theme, and they have other metrics that they want to score highly on that they're not exactly training on. And so we see we're pretty competitive and can outperform some of the existing baselines for diffusion-based models to do this. And I expect these results to get a lot better because we did these 8 hours before the deadline to iClear. So this is why we're waiting on putting this online, just because it's important that we release good code and also, do everything neatly and do the best we can. Okay. So that's kind of all I wanted to tell you about. I think why I'm excited about this is the pros is it doesn't require any gradients of these rewards. You don't need to back propagate through trajectories that you've generated to solve the problem. So it's very directly amenable to using flow map models, which are these one-step models that we've also been pushing with Nick Boffey and Eric van den Eyden and some people at NVIDIA, Karsten Kreis and Amir Mushtaba, and then Mir Sabor. And yeah, the other thing is the loss is just this regression objective. And so what you actually can show by playing with this control variate thing I was discussing above is that the variance is actually better than just doing flow matching itself, if you can proceed this way. So I guess an open question is how would you actually choose the best control variate for any h? And can you learn that adaptively or estimate it in an efficient way to sort of improve this algorithm? And we'll put this online hopefully later this week. And just want to congratulate Peter and Brian for a really awesome effort to get this out the door. So thank you very much for listening. Happy to chat.